Welcome to Cookie's Maths and Science Hub. Today we'll be looking at the concept of half-life when talking about radioactive decay. So, what do we mean when we say half-life? As time passes, less and less of a radioactive isotope will be present, and the levels of radioactivity decreases. An interesting and useful aspect of radioactive decay is the half-life of a substance. The half-life of a radioactive isotope is simply the amount of time it takes for 1/2 of that radioactive isotope to decay. The half-life of a specific radioactive isotope is constant, meaning it is unaffected by the conditions around it and it is independent of the initial amount of that isotope. What this means in practice is, if you look at our graph on the right here, if we start with 100% of something, after one half-life we'll have 50% of that amount of substance. After another half-life we'll have 25%. Another half-life 12.5%. That is, it's half of what remains, rather than half of the initial amount over and over again. Half-lives for radioactive isotopes can vary greatly, from minutes and seconds to a number of years. Here's a few examples of real-life radioactive materials and their half-lives. Uranium-239 has a half-life of roughly 23 minutes. That means if you had a 1 kilogram amount, after 23 minutes, only 500 grams of that would still be uranium-239. Carbon-14, on the other hand, has a half-life of 5,730 years. That means it's going to take a little bit longer to see it start to decay into large amounts. Finally, iodine-131 has a half-life of 8.04 days. Now, it's important to remember the half-life concept, that is, after one half-life, half of it remains the same regardless of the length of the half-life. It simply changes how long it takes for that half to decay. Below is a visualization of this half-life process. So, iodine-131 has a half-life of 8.04 days. It decays via beta decay into xenon-131. So at 0 days, you can see here we have 8 particles or atoms of iodine-131. After a single half-life, 4 of them have now decayed into xenon-131, and the electrons are floating around in that space as well, as it decays via beta decay. Remembering, beta decay is simply the ejection of an electron. Now, after another 16.08 days, not another 4 decay, but 2 decay, as that is half of what there was at 8.04. The important thing is to remember the half-life is simply how long it takes for half of whatever's present to decay. That doesn't mean it's half of the initial amount, it's half of whatever is present when it ticks over to that new half-life. So at 0 days we had 8, at 8.04 or 1 half-life we had 4, then at 16.08 or 2 half-lives we had 2. So it's halved and then halved again. Important to note that in this case, this is one of those few examples when we talk about radioactive decay, this xenon-131 is actually still unstable and will decay via gamma decay following this process. We haven't shown that here as we're more focused on the iodine decay and talking about half-life, but it is something important to remember. So, let's look at a few practice problems now and how we would be required to solve these in physics and chemistry. Uranium-239, as we've stated, has a half-life of 23 minutes. If we have a sample of 960 grams, how much would we have after 138 minutes? Now, there are multiple different ways we can solve this problem, but there are 3 clear strategies that are often used. First things first, we should find out how many half-lives it has gone through. So, we simply do that by taking the amount of time, in this case 138 minutes, and dividing that by its half-life length. So 138 divided by 23 equals 6. Therefore, it has gone through 6 half-lives. As I said, there are a few ways we can then solve this problem. One of the easiest ways, and the way that most people learn how to do it first with half-life, is simply to half and half and half and half and half. That is, to half it 6 times, because it goes through 6 half-lives. So if we start at 960 and we divide it by 2, or half it, we get to 480, and we know that's 1 half-life. It then goes through another half-life, so we half it again. 480 divided by 2 equals 240. Do it again. 240 divided by 2 equals 120. Do it again. 120 divided by 2 equals 60. Once more, 60 divided by 2 equals 30. And finally, 30 divided by 2 equals 15, which is 6 half-lives. Therefore, after 138 minutes, 15 grams remains, as it has gone through those 6 half-lives. Let's look at the 2 other strategies now for how we might solve this same problem. Another way you can solve these problems is by using a very simple mathematical formula. That is, the amount remaining is just equal to the initial amount times 1 over 2n, 2 to the power of n, that is, where n is equal to the number of half-lives. As we already found out, this has gone through 6 half-lives. So therefore, our amount remaining is equal to 960 times 1 over 2 to the 6, which gives us 15 grams. Obviously giving us the same answer. As I said, these methods all get us to the same point. It's just different ways of doing them. Now, this is the basis of the half-life formula, which is shown below, which is A, which is the final amount, is equal to A initial, which is the initial amount, multiplied by a half to the power of t, which is the time elapsed over the half-life. This formula is obviously a bit more complex and requires a few more steps, but is very important in usage in more complicated half-life problems, which require some logarithms and some more complicated maths when you're working backwards. That is, if you're trying to find the half-life or how much time has passed from a given example. Now, what we're going to do is we're going to look at one more example, and I'm going to go through all 3 methods for how you might solve the problem using just the half and half and half again, the simple formula, and the more complex half-life formula in total. So, carbon-14 has a half-life of 5,730 years. How much would remain if I started with a 565 gram sample after 17,190 years? So, let's start with our first method first, half and half and half again. So, we first need to figure out how many half-lives it's gone through. So we take our total number of years, 17,190, and divide that by our half-life, in this case, 5,730. We can keep it in years because they're both in years. Obviously, you need to make sure they're in the same unit before dividing. So this equals 3, so it's gone through 3 half-lives. So then all we need to do is half it 3 times. So 565 divided by 2 gives us 282.5. Divide that by 2, we get 141.25. And divide that by 2, we get 70.625. Therefore, after 17,190 years, 70.625 grams remain. Looking at our second method now, which is the amount initially multiplied by 1 over 2 to the power of n, where n is the number of half-lives. So once again, if we're using this method, we need to find the number of half-lives. So we go through the same process and find that we have 3 half-lives. So our final amount is going to equal our initial amount times 1 over 2 to the power of 3. So our initial amount is 565 times 1 over 2 to the power of 3, which gives us the same answer as we stated, 70.625 grams. Therefore, 70.625 grams remaining after 17,190 years. And that's our method 2. You'll notice this is a bit quicker, but you've got to be careful as it can only be used for certain examples. Finally, our method 3 is using the full half-life formula. That is, final amount equals initial amount multiplied by half to the power of time taken over the half-life. So, the good thing about this formula is, this will work for pretty much every half-life example, and you can simply substitute your numbers in. So our final amount is going to equal 565 multiplied by a half to the power of 17,190 over 5,730. Now you'll notice here that this is simply, if you look closely, it's actually the same as method 2. Method 2 is just this shrunken down. So instead of this one where it calculates that n value for you, because we've put that in that power section there, that's effectively calculating our n value. We're just skipping that step by putting all the numbers in. So it really is just method 2 extended out into its truest form. Chucking that all in your calculator or doing it in your head if you have such a quick maths brain, A, or our final amount, is equal to 70.625 grams. Therefore, 70.625 grams is remaining after 17,190 years. The important thing to note is all 3 methods give the same answer. In a test or anything like that, you wouldn't necessarily be marked down unless you're asked to do it a specific way. So you can always check your answer by using one of the other methods. And as I stated, as you get a bit more familiar with method 3, you'll see that it is very much just method 2 with a few easier steps, because you can just put the numbers in rather than having to find your half-life first. Thanks for watching. Hopefully now you have a good idea of what half-life as a concept is and how to calculate it through the examples shown. Be sure to like and share this video and leave a comment for any future content or any questions you might have. Please be sure to subscribe to the channel and we hope to see you back again soon.